Okay, guys. Okay, so yes, here's our plan. Our plan is you know, our thinking is that P groups seem to have a lot more structure than just the average finite group. But what we can do is there's kind of like a systematic way to understand the subgroups of a finite group that are also P groups. Okay, so our plan is to understand that. Okay, so let me tell you what I mean by yeah. So what is first of all, let's define a C log P subgroup. A G be a finite group. Okay, let P be a prime. And then suppose that the order of G, number of elements of G, is like P to the K times M, where P does not divide M. In other words, like M has no factor of P. Okay, and P does not divide M, and K is greater than or equal to 1. Then a C log P subgroup of G is a subgroup H of G such that the order of H is P to the K. Okay. So this is definition of a C log P subgroup. Okay, if you think about it, out of all the subgroups of G, which are P groups, this is the largest possible size a subgroup could be. That's a P group. Okay. Okay, so our plan now is to basically to state and prove the C log theorems. The first C log theorems just says that a group G like this has a C log P subgroup. Okay, so that's our first goal is to show that C log P subgroups exist. Okay, so our first goal, C log P subgroups exist. Second goal is to say C log P subgroups are all conjugate to each other, which is very special. And the third problem, basically the third Syllabus theorem says, allows us to calculate the number of Syllabus P subgroups. Okay, well, I see this is kind of a little bit fuzzy or something. Okay, and this is very special because these theorems apply no matter what crazy group you come up with, as long as it's finite. Okay, so if I tell you I have a group with, 10,053 elements or something, well, you do need to factorize 10,053, but once you do that, you can say a lot about the structure of the group without actually knowing anything else about the group aside from the number of elements. Okay. So our plan is to at least state the Syllabus theorems, prove them, and also do some apply these theorems to some examples of groups. Our plan for the near future. Okay, definitely today we can at least state these theorems and go from there. Okay. Our first goal is we have to prove that Syllabus subgroups exist, and basically our proof is by induction. And the first step of the induction, you could view it as the following theorem called, what is this? I guess this is Cayley's theorem. Cayley's theorem. So let G be a finite group. Suppose P is a prime and P divides the order of G. Then G has an element of order P. Okay. Okay, you can kind of think of this as like kind of like a converse to Lagrange's theorem. Let me just remind you of Lagrange's theorem. Lagrange's theorem says that if H is a subgroup of G, then the order of H divides the order of G. And now we're saying if we have a prime number dividing G, there's an element with that order. So Lagrange's theorem says that if H is a subgroup, then the order of H divides the order of G. And we're saying that if a prime divides the order of G, then there exists X with the order of X equals P, and then that X will generate a subgroup of order P. Okay. Okay, so this is like the reverse order. Like you start with a divisor of G and you get a subgroup of that order. Okay. So let's prove it. There's a lot of proofs of this one. because we're studying group actions, I want to look at the proof, which is using group actions. Okay. Okay, and actually I just want to set up this theorem, like the strategy for this proof. And in the assignment, well, one of the assignment questions will be to fill in the details of the proof. Okay. So the proof, except it won't be complete, but the proof is, let S, this is going to be the set that our group acts on. The set S is going to be the P tuples G to the P, right? So P tuples of group elements such that when I multiply them all together, I get the identity. Okay. And this is our set, and then we also need a group, and in fact, we don't use G, we just use, remember, so we let the cyclic group with P elements. This is the group generated by A, satisfying A to the P as the identity. Act on S by, I'll put, yeah, A times our P tuple, say X1, X2, up to XP in S. So A acts on this P tuple by just shifting everything to the left. Yes. Okay. So shifting everything to the left and then putting the first thing at the end. Okay. So notice I've told you what the generator does to each element of S. So that tells you what every element of the group does to the elements of S by because, you know, if A shifts everything over to the left once, if I do A and then A again, I've shifted everything over to twice, you know, so A to the I times X1 up to X to the XP is just, well, you shift everything over I times. So I guess you have an XI plus 1, XI plus 2, and then you have, at some point you have XP and then X1, and then the last one is XI. You shifted everything over to the left I times. As long as I has to be between 1 and P. Okay, and notice as long as this is in S, this is also in S. Notice if X1 times X2 times XP is the identity, then multiply on the left and right, multiplying on the left by X1 inverse and on the right by X1, you get x2 times xp times x1 equals x1 inverse x1, which is the identity. And that means that x2, x3 to xp, x1 is in S if x1 up to xp is in S. Okay, so now I have my group, the cyclic group with p elements acting on S. So CP is a p group. It's a group with p elements. So what that means is, so the number of elements of S is congruent to the number of elements of Z modulo P. Okay. And then here's where I'll start leaving things for you to do on the assignment. So, okay, so what we have now is that I'll just state as a fact, the number of elements of S is the number of elements of G to the p minus 1. Yeah, this video is a little bit blurry. Sorry about that. Okay. Another fact, also P divides G. So the number of elements of S is congruent to 0 mod P. So the center of the group action is congruent to 0 mod P. Okay. And then another fact, is that x1, x2 up to xp is in the center if and only if x1 equals x2 equals xp. Okay. And another fact, the number of elements in the center of this group action is greater than 0. Or sorry, is let's say greater than or equal to 1. This says the number of elements in the center of this group action is divisible by P. So the conclusion is so everything in the center, there exists some element of S where A is not equal to the identity. In other words, like the elements of S are the things where you multiply them all together, you get the identity. So this means that A to the P is the identity, but A is not equal to the identity. In other words, the order of A is exactly P. Okay. And we'll see, like, the details are in the notes and also to be worked out in an assignment question. Okay, so now we know that, I can say, like in a group with 105 elements, there is an element of order 7. there's an element of order 5 and there's an element of order 3. All right, so example, let the order of G be 105. Now that's just 3 times 5 times 7. Then there are elements of order 3, 5, and 7. I don't even need to, I don't even need to investigate like the structure of the group or anything. I just get that immediately from the factorization of G. Okay. Okay, so we can think of this as like the base case of Sylob's first theorem. And we want to prove the theorem by induction, so that becomes this next proposition. Let G be a finite group such that P to the K divides the order of G. Then G has a subgroup of order P to the K. Okay. And our plan is to prove this using induction. Okay, so let me try and state exactly what is our, what is the statement we're proving? So P of n is a statement that, okay, it's a statement that if G has order n and P divides n, and P to the K divides n, then G has a subgroup of order P to the K. Okay. Okay. So we're going to prove P of n using strong induction. So there's like several different base cases. Okay. First, note if K equals 0, then we're asking for a subgroup of order P to the 0, which is 1. We're asking for a subgroup of order 1, which is just, we can just take the trivial subgroup. Take the subgroup, the trivial subgroup. Okay, so from now on, just assume K is an integer bigger than or equal to 1. Okay. Okay, so our base case is that is the property when n equals p, right? Because the when k is bigger than or equal to 1, the property for integers like the statement is trivial until you get to p. Okay, so let me just say in brackets p of 1, p of 2, up to p of p minus 1 are trivial since p to the k cannot divide any number between 1 and p minus 1. Okay, so our base case is the case when n equals p, and so in this case G has p elements, and we must have, in this case, that p to the k equals p divides p. So sorry, we must have that p to the k divides p, which means that k equals 1, and we can take our subgroup to be the entire group. Okay. And again, we're trying to prove the proposition that assuming p to the k divides the order of G, and the order of G has order p, then G has a subgroup of order p to the k. Under those restrictive conditions, k has to be 1, and so we can take just H to be in the entire group G. Okay, so now we do our strong induction hypothesis. So assume for some n greater than or equal to p, we are going to assume p of 1, p of 2, all the way up to p of n. And now our goal is to prove p of n plus 1. Or induction step. Okay. Let G have order n plus 1. And suppose p to the k divides n plus 1. If p to the k does not divide n plus 1, then the proposition is kind of vacuously true. Because the proposition says if p to the k divides the order of G, then G has a subgroup of order p to the k. So if p to the k does not divide the order of G, it's not saying anything. So we can stop. Okay, so p to the k divides n plus 1. And we have to construct a subgroup of order p to the k. Okay. I think okay, I think before we really get started with the induction step, it's a good time to just take a break. But let me just, before we take a break, let me just tell you, we're going to divide our induction step into 2 cases. One case, we're going to say that like we can find a subgroup H such that, or sorry, a proper subgroup H such that p to the k divides the order of H. And then in that case, we can apply the induction hypothesis to find a subgroup of H having the right order. And the other case is that no proper subgroup has P to the K dividing the order of H. And then we can do some tricks to get rid of that case. Okay. So more on that in the bottom of the last page. Yes, I can. So I'll turn back to the bottom of the last page, and then we'll take a break for or maybe like 7 minutes or something. Okay, here we go. Is here where you wanted to see? Okay. Okay, so yes, let's come back at about 1:25. And after the break, we'll finish this proof. And then probably we just have enough time to state the other two Syllabus theorems. And that'll probably be it for today. Okay. Okay, so see you guys in about 7 minutes.